So I am going to start again, or rather, I would like to continue our discussion on transformer. But before we start, let us make things very clear regarding our representation. In my past few videos, I have sometimes casually used capital letters, sometimes use all letters, but here henceforth we will use small letter to indicate instantaneous values, and capital letters will be RMS value, right? And maximum value will be denoted by and for average value with subscript DC, right? Now with this, let us start our analysis. And before I proceed, let me write the important formula. Point number one. Okay, before I write the formula, let me write another few things like N1 primary turns into secondary turns N3 tertiary turn V1 impressed voltage V2 secondary voltage I1 primary current I2 secondary current I3 tertiary current Now, one more thing, that henceforth what will be used to represent equivalent representing core losses. Branch reactance, then we will have so in addition we will have our we will have R1 R2 winding resistance and X1 X2 linkage reactance. Now, in addition to all this, we will have formulas like first formula we can write it like that reveals this is a very important formula. What it states that at any instance MMF produced by primary winding and MMF produced by the secondary winding better to write here at any instance algebraic sum of MMF produced by primary winding and MMF produced by the secondary winding is equal to the instantaneous value of no load MMF. This one also known as MMF balance equation. However, if we compare the magnitude of I naught with I1, we will find So when I naught is I generally at max 3 to 5% of I1, and that is how, or in some cases, or means I naught is even smaller. So this makes us indicating magnitude wise and also if you consider this equation, if you consider I naught magnitude is negligible, you can write that there will be, okay, from this one we can write another equation that is very important for us, like if you write it equation 1, then if you perform side transposition at equation 1, then you will get I1 is equal to I naught minus into by n1. This instantaneous Phasor vector sum, but the same relation holds good in Phasor also. In Phasor you can write I1 Phasor is I naught I2 dash, right? So this one, this is very important. This is our Phasor relation. Sorry, this should be minus. Sometimes we call this as, this whole thing as our, let us draw the exact equivalent circuit of the transformer first, then I will try to write the equation, because in light of that we can Now see what exact for this circuit, what equation we can write for magnetizing branch. We can write, if here is the current IH plus E and in this branch it's I mu, we can write IH plus E is equal to minus E1 by R naught and I mu is equal to minus E1 by Jx naught. This is equation 2, this is equation 3. Here at this point, whatever KCL we will get, we have already written it somewhere in the last page probably. Yes, this one. I1 is equal to I0 minus I2 dash. So, here this is the case, then we have to write other important equations. What are those equations? Those equations, if you try to apply KVL at the primary side, you will get V1 is equal to I1 R1 plus JXL1 minus E1. This is equation number 4. Then what is equation number 5? Equation number 5 is V2. Let me draw the load also, otherwise it doesn't make much sense here that how I2 dash current is flowing. Here we have the load. Here we have the load. So for load side it is V2 dash is equal to I2 dash R2 plus JX L2 plus E2 dash. So equation number 5, if you have some difficulty, you may ask me the question. This equation, what I have written, that can be written in a reverse way, like, see, what is V2 from the direction of current, V2, you can write it like this. The same equation, we can write it like minus E2 dash is equal to minus I2 dash minus V2 dash yes. So from this equation it gives us E2 dash minus I2 dash R2. Here it also. Sorry, I'll surely let you know what is R2 dash James Q2 dash, how they are coming. We will discuss shortly. Okay, so now here one more thing that is very important to note, that here all these, there are how these all these dashed line, dashed means dashed voltage, dash current, dash parameters, all these are referred to primary side. Similarly, we can have referred to secondary side also, that is not a big deal. Now, how this referred to primary side is coming, for understanding that, let us try to analyze a few extra things. Like what gives our E1 and E2? If you see the instantaneous value of primary and current voltage, primary induced voltage is that is minus n. Now, if we neglect leakage, E2 is neglecting leakage, so we from this we get E1 E2 is equal to N1 by N2, and as the amount of leakage flux is very small, we can still have this approximation U1 E2 is equal to N1 by N2 in all conditions. The RMS value of induced EMF is proportional to the ratio of this is proportional to N1. Similarly, our one more assumption says we have our R reluctance of the core should be very small, so if reluctance is very small, then if you can recall the first lecture on transformer, you will see that your MMF by reluctance gives us that value of flux, while the flux is again somewhat proportional to as for a given source, this is constant, given source. So for constant supply condition, flux is almost constant. That is why transformer is known as constant flux machine. Now, if your reluctance is very small, you need a very small mmf. Is required to reach the saturation value. Now, if small mmf is required, it implies I naught is, that is magnetizing component, is very small, and that further implies I1 magnitude wise is almost is equal to I2 dash, or if we write that equation, then we can write N1 I naught plus N2 I dash, N1 I1 plus N2 I dash is almost is equal to 0. So that leads I1 by I2 is equal to N2 by N1 if you consider only the magnitude part. This will give you this relationship. Now, from this relationship, it is evident that we are having E2, E1 magnitude wise they are into N1, then we are having I1, I2 magnitude wise they are proportional to N1, N2. In addition, as we know that I naught is very small, and it can be shown that our voltage that we are having here, like we can show that for an ergonomically designed transformer that is having a very small value of series resistance or series component, this drop is 3 to 5%. Most of the cases it is 3% of V1, and similarly this side drop is also negligible. So if these two drops are negligible, then we can write V1 is approximately equal to E1 magnitude wise, and V2 is approximately equal to E2. I am several times repeating this word magnitude wise, so don't get confused with the Phasor sign. We are here only considering magnitude wise. So if we consider that magnitude wise, we can write here that this relation implies V1 by V2 is equal to and from that we can see that whatever is your V1 I1 product, that same will be V2 I2 product more or less. This gives us the relation that transformer is a constant kVA machine, and we rate transformer in kVA. Now, one more thing here I would like to mention, that it is not only about this ratio. We have to consider the component transformation, like series parameters that are Let me write the equation once again. It is V1 is equal to minus, not minus, it is plus I1 R1 plus JX L1 minus E1 V2 is equal to minus I2 R2 plus E2. So if these relations hold good, then one thing is very important, that when we will try to transform our primary component to secondary, what we will have, this equation should be written like this. Like in primary, if we define n1 by n2 is equal to a, so in that case we will have all these terms transformed to our primary side, and this will lead us this relation R1 that whenever we will try to refer a secondary quantity to primary side, it should be like or a square R2, and similarly for XL2 it should be N1 by N2 square XL2, right? So all these are very important equation, and that gives us the Phasor diagram. What is that Phasor diagram? Once again I am writing this equation. Several times I am writing this not to make you bored, but to make you understand clear and complete. So this side can further be written like this. Both are equal, means both are equivalent. Not equal, they are equivalent. So what is the idea when you connect a transformer with a load? Here you have your load ZL. Now you measure voltage across ZL. You measure voltage across. Let me check whether it is recording or not. Yes. Voltage across ZL, then it is current through ZL, and then it is power consumed by ZL, and all this together gives us the power factor angle for a given load. Now once we know all these things, then we will try to find out the primary side phasor direction. So primary side phasor relation, what we will get, get that is this one will be validated. Now draw the phasor diagram. Phasor diagram will be like this. We start with V2. Let us consider it is a step down transformer. We have I2. I got this angle from the mentioned calculation. If I know what is the value of R2 and JXL2, then I can add them. This is my I2 R2, and parallel to that I should draw I2 XL2. This is my I2 Z2, and when I connect, this is my V2, and when I connect it, I got E2. Now E2 and E1, they are collinear because they share the same relation with the same vector. So this is my E1, and we get this by using this relation. Then we can draw minus E1. Then from minus E1 we will get here that value. That is small this is small, not pencil sound not working. Anyway, it will be IH plus E collinear with minus E1, and then I mu, that is lagging this, and then we will have this is my I0. Then with I0 I have to add this I2 dash minus I2 dash, better to say. So minus I2 dash will be just 180 degree. What about minus I2 dash will be just 180 degree out of phase with I2. So this will be something like this. So once we get this, then if we join the tip of this minus I2 dash with our origin, we will get our I1. This is our I1. So I1, then we have to add I1 R1, then with that we will get JI1 XL1, and when we join we will get V1, right? So this is our complete phasor diagram already discussed. Now we will move to approximate phasor diagram and approximate equivalent circuit. Please note that whatever I have discussed till now, it is exact equivalent circuit. This one is known as exact equivalent circuit. And now we will move to our approximate equivalent circuit. So let us move to our approximate equivalent circuit. What is that approximate equivalent circuit? It is very easy to understand that approximate equivalent circuit is something like, the basic idea is that drop across our series branch. We know series branch voltage drop is actually what I am trying to mean by that series branch voltage drop. Let me show the circuit once again. Yes, this drop is 3 to 5% of full load voltage when it is the transformer is drawing full load current from the source, and we can understand drop across this series branch is proportional to the current I1. So here, if this is the case, then what we can do, that means irrespective of its loading condition, or we can say that at the highest loading condition our E1 is 97%, means E1 cannot fall below 97% of our supply voltage. So we can write magnitude wise V1 and E1 are equal. I am talking about magnitude wise. So if that is the case, then what we can do, instead of considering it as a means, what we can do, let me draw the diagram once again, otherwise it makes things difficult to understand. So across this we got this E1. So what we can do here, if this is our V1, since this one is at max 0.03 V1, we can shift this branch here, and shifting that branch result in what? Shifting that branch result in this. Shifting this branch result in having some trouble in deleting this one. Yes. Let us go to the next page. It unnecessary was a wastage of time. Shifting of this branch let me write, it is our approximate equivalent circuit. So shifting of branch, it results like this. This is our R2 dash JXL2 dash R1 JXL1. This is our V1. This is our R0. This is our JX0. And here, this side we have our secondary side. So, how this approximation helps us? This reduces the complexity of this calculation to a great extent. See, for this modified circuit diagram, let me write down the equations once again. We will have I1 is equal to I0 plus as usual. Then however, what about I0? I0 is plus IH plus E. Now these two can further be written like V by R0, V1 by R0 plus V1 by Jx0. And here we can write for the secondary side, what we can write here, we can write that all other equation remain same. We get V1 is equal to I2 dash R1 plus JXL1 plus R2 plus JX2 dash plus V2. Now here you will have a trouble. Why trouble? Because the way we have represented it, if we go to see, if I write it like this I2 dash, if I show the direction, then it seems V2 is having a higher potential, and that is what drawing a current towards this V1. So what we need? We need a bit more sensibility while dealing with this approximate equivalent circuit. How can we make it a sense, like what is our receiving end and what is our sending end? This, if we consider it as a system, then this side, this if we place this whole this whole approximate equivalent circuit inside a box, right? Then this side is my receiving end and the other side is my sending end. So what it should be like that, means or forget about sending and receiving end, that will make the whole discussion more complicated. Think about who is receiving power. The power is received by your primary site, and then who is where you are supposed to transfer that power, that is through secondary site. So there will be some, in case of normal loading, there will be some drop, that means normal flow of current irrespective of it should be in this direction. So what we can do, what change we can incorporate, that okay, we understand that this one is also correct, that N1 I1 plus N2 I2 bar was N1 I0. But this is why this confusion, not confusion, this is also true. This gives us an essence that this, if we consider this as our demagnetizing MMF, this gives us the magnetizing MMF, and this one as required MMF. Now, instead of considering the current that is flowing from the upper terminal of these two, means instead of considering current is flowing in this direction through our upper branch, what we can do, we can just modify it in terms of phasor and also in terms of our physical circuit, and that is quite rational. That current is flowing from this upper branch, from this V1 to V2, right? So what we can do here, without violating anything, it is just a matter of representation, how you want to represent. We can write I1 is equal to I0 plus I2 bar. Now if you insist that sir, now we are not happy, we want that our previous one, this is what I have written in the current one, and the previous one was what? This was our previous equation. Now if you want this, then for the previous circuit, how should we represent? We should represent it like this, not here. You have to write it like that. Then here is, and this one is this current is. So here you will have a current in this direction, that is minus I2 dash, and by doing so you can write I2 dash R1 plus Jx1 plus R2 dash plus Jx2 Jxl2 dash Jxl1 minus V2. Basically, why this minus sign is coming? Because if you go back, so this makes the whole discussion very weird. Why this is? This makes everything very difficult to understand. That here, if you see, let me clean this whole thing once again to make it somewhat understandable. Now at least successfully I could delete a portion here. So what is the point here? Point is very simple, that if we go back to our previous slide, here you will see the whole thing, this weird thing. Yes, even from this one also we can explain. Your V2 was related to E2 dash, and E2 dash was collinear with E1 dash. However, V1 was almost out of phase with E1. So while you are trying to make them means like this, then obviously it will make you or give you a sense that V1 and V2 are 180 degree out of phase. But if we want to represent it in this way, for sake of our representation, and forget about the polarity of induced EMF, and if we forget the polarity of induced EMF, then what we can have? We can have a simple things like this. Here we will have R1, Jxl1, Jxl2 dash, R2 dash, and here you are giving V1. Here you are getting V2. Positive V2. Now, a few questions you will ask, sir, just like our previous Phasor diagram, what you have discussed, it is like V1 and V2 must be 180 degree out of phase. But here you are claiming or trying to draw the Phasor diagram as if V1 and V2, they are almost in same phase. So, which one should we consider? The idea behind it that, see, V1 and V2, try to understand it very clearly. V1 and V2 phase relation depends on the polarity of the transformer, because they are the outer terminal. What is polarity I will explain. For the time being, I just want to make you understand by saying what is polarity, that somewhere I have drawn a transformer. Yes. Here, if we have identical polarity, then what you will have, if when when your this terminal will have positive or means positive value with respect to this terminal, here also you will get same. Means we can just by means of dot convention. Dot convention indicates the direction of current flow. So if your dot means are like this, then you will have, for the position of dot, you will have the difference in your current flow, right? Just a minute. So what happened, suppose if you have there is some problem here in my device anyway. So what happened, suppose for one terminal, say we write it like H1 H2 and it will like be X2 X1. Like if this one H1 H2 is means H2 is having means H2 voltage with respect to H1 and X2 voltage with respect to X1, they will have identical means voltage. Like if at an instance you are considering an alternating wave, right? This is your alternating wave. So if you take an instance, at that instance it may happen that voltage across and this difference will appear across your H1 H2. So it may happen that H1 is at this polarity and means potential, and H2 is having this. So proportionally what you will have here, you will have different voltage waveform across this your secondary, but that will also maintain the same. Like it will, you can have a thing at that same time, you can have like this. This is also called subtractive polarity. We will discuss it later. Like you will have X2 X1 here. Now the issue here is that what I was trying to say by doing all this, that V2 V1 polarity, it totally depends on the polarity of the transformer, and more specifically polarity of the transformer depends on how you wound your winding on your core. So it has nothing to do with our Phasor diagram apparently. So there will be no harm. As long as you are considering E1 separately, there is a problem. If you try to place E1 and V1 in same phase, that will try to violate some basic understanding. But there is no harm if you place V1 and V2 in same phase, because direction of V2, it is not only the induced EMF or means how the induced EMF is generating, but it is also depending on the nature of turn. If your primary and secondary both are wound in a particular direction, you will have a particular voltage waveform appearing across your secondary. And if it happens that primary winding turn is from turn has been done in clockwise manner, and while the for secondary it was in anti-clockwise manner, then you will have a voltage phase difference in your primary and secondary. So this terminal voltage, in a nutshell, why I am telling all these rubbish, because in a nutshell you should have no difficulty in accepting the fact that V1 and V2, they can be represented in the same phase or they may be in opposite phase, but for our case we can always accept that V1 and V2 are in same phase. We assume that our transformer winding direction, winding when the transformer was manufactured, it was done in such a manner that V1 and V2 they become collinear. And if with this, if you want to make V1, V2 collinear, or means not collinear phasor, but rather more or less they are almost in phase, then what you will have here, you have to modify your current accordingly. And how these two currents are not also violating the things, what now, previously what I was trying to say, I was trying to give you a flavor of, probably I have written it somewhere, that the additional primary current and demagnetizing current, when we add them together, considering their direction, the algebraic sum, they give a very simple thing, that is the magnetizing component of current required to maintain the core saturation. But in case there is also nothing wrong to represent here like this, that I naught plus I2 dash, it is also reflecting the magnitude. Here I2 dash, you can say previously I2 dash was flowing in this direction, means I2 dash was inward, and now we are drawing I2 dash in outward direction. But this whole idea, this whether I2 dash will flow inward or I2 dash will flow outward, it also depends on that the way how you own your transformer. If you are, see, like the very basic understanding of phasor, the direction of current flow and everything, we must keep it in your mind. We are not dealing with a DC circuit, it is an AC circuit, and everything depends on the relative potential. So if V2 is an even, means V2 is in your load side, but if V2 and E2 they are having a value that means V2's potential is higher than E2's potential, then current will try to flow in that direction. There is no harm, and it is obviously it is possible. Now when we are trying to place them in this way, then this will make a perfect sense that where is the cursor? Yes, when this one, this is a reflection of the secondary current. Once we make this reflection of the secondary current 0, there will be primary current will be equal to just the magnetizing branch current. And if we load the transformer, then there will be more this one. So we would like to modify our means total equivalent circuit in this way, and accordingly we get a relation between V1 and V2. And what is that relation? Relation will be like very simple relation we will have here. After this shift and all this mambo jumbo we have done here, we will have something like V1 is equal to what is it? Here you have to consider the phasor relationship, and you can find out the regulation also using, and that I naught will be very easy to find. I naught will be how much? I mu plus IH plus C, and IH plus C you can find it by V1 by R naught, and I mu will be V1 by X naught, right? And with this we will solve some numericals and also see when how we can conduct open circuit and short circuit test, and also we'll discuss about regulation formula. So henceforth we will use this approximate equivalent circuit. Now you may ask me, or you may even in my absence use some passwords to means that what is the point of means spending so much time on the sign of E1 and exact phasor diagram, because we are after this we are not going to use this exact phasor diagram anywhere. But the idea behind drawing that exact phasor diagram is to make you understand that how things in physical world happens. It is not that whenever you apply voltage, suddenly at the same instant you will get some instantaneous voltage across your winding. When I discuss AC winding video, AC transient video, you will get more. I'll shed some more light on that topic. But means things you must understand. It is not only that for the present moment what is required or not. What we have discussed for transformer understanding the exact phasor diagram, the same phasor diagram will help you to draw phasor diagram for synchronous machine, phasor diagram for induction machine. Everywhere you will get benefit from that. So that is why it was important, right?